So we start off. So we continue with our review of essentially the list of things that we will not do in this course. We continue with that, and so once you have the no cloning theorem, you we can then discuss about quantum teleportation. I mean, I will not discuss it. I'm assuming that you know quantum teleportation. The point that I want to make is that quantum teleportation has essentially has a reduced importance if you don't have a no cloning theorem. So, because if you can clone, then you can find out what the state is locally from a single copy and then send it by a phone call. There is a catch there that sending the phone call will still require an infinite amount of communication, because an arbitrary two-dimensional system looks like this, something like this, or more particularly it looks like this. This is the so-called block sphere or the Poincare sphere, depending on whether you are coming from optics or from spintronics. This theta is a real number, yes? It has a range, and this phi is also a real number. And you have to send these two real numbers over a phone call. This will require an infinite amount of communication. Yes, because an arbitrary real number is an infinite number of points, infinite number of decimal points. Barring that, if we even ignore that, this thing is not possible because teleportation works at the single copy level, and at the single copy level one cannot clone, and since you cannot clone, there is no option of knowing the particle here and then sending it by phone call. This was, well, you know, this is in 1993, and it forms one of the pillars of the subject, especially of the subject of quantum channels. The things that we assume to know about one can roughly say QIC near foundations of quantum mechanics. The most prominent one is, of course, the Bell's inequality or the Bell's theorem. And which says that quantum mechanics is inconsistent with any local realistic theory. But Bell inequalities have obtained further importance later on beyond its foundations, like it's the entanglement witnesses are essentially, well, the opposite. The Bell inequalities can be thought of as an inefficient entanglement witness. So if you look at the separable ball, and this is the set of all states, a good entanglement witness, an optimal entanglement witness looks like this, something like this, a linear one. Bell inequalities are also linear witnesses, but they are typically heavy. It's never on this side. Yes, they're always witnesses, but it's typically away from the separable ball. Not always, but sometimes. So when we are talking about Bell inequality, we are talking mainly about this CHSH inequality, which is different from the original inequality. And we also assume that you know the EPR paradox, and we also assume that you know this Chirelson. There are several spellings for this. Chirelson's bound. This TS is sometimes written as C. I don't know the pronunciation, it's probably some Russian person. And then the Hordejki formula in 2 cross 2, which is that if you take this CHSH inequality, what is the amount of violation, the maximum violation by the CHSH inequality by an arbitrary state, pure or mixed, in 2 cross 2. This was given quite early by the Hordejki's, 96, I guess. Paper in PLA, physics letters, they forgot the year, around 96, I guess. This has been generalized into what is called Weinfutter, Werner, Wolf, Zukowski, Bruckner inequalities, which is, this is in 2 cross 2, this one is in 2 cross 2 cross up to n. In this case, here there is a necessary and sufficient condition. In this case, there is also a necessary and sufficient condition, maybe slightly more complicated than this one to handle it. But in both cases, one finds. But these are so-called correlation function inequalities. So by what is a correlation function inequality? By that we mean that we take an observable here, we take an observable here and so on. So let us call them A1, tensor, A2 and so on up to AN, and we take the state rho, and this is called a correlation function when none of them is the identity operator. Then we call it a correlation function. Bell inequality, the CHSH inequality, if you remember, looks like this. In particular, it does not have the local magnetizations in this. So so in 2 cross 2 it is known that there are 4 inequalities that forms the whole space, that defines the set of quantum states that satisfies the Bell inequality. In this case, it's of the order of 2 to the 2 to the n. So, for those of you who were there in yesterday's quick dinner, I am trying to guess, because there was a 2 to the n for n qubits also in yesterday's talk. I'm just trying to guess whether it has the same origin. I would guess yes. There are a lot of interesting facts on Bell inequalities that were proven during the 90s and also in the 2000s. In particular, Perez showed an example where if you have a state that you can have a state that satisfies Bell inequality, but you take 2 copies of it, it violates the Bell inequality. Bell inequality.
What does that mean?
So he showed that this state, call it A, B, prime, this was 96 or something, I forgot the exact year. It's that these two states are the same states. This is rho in 2 cross 2. Both of them satisfies this inequality. So you can give a local realistic description to it. But if you take them together, you can write a Bell inequality for in this space and in this space, and it is valid.
In 4
So it's not an additive quantity, yes?
In 4 cross 4.
In 4 cross 4. Popescu gave another example of a state which is already in higher dimensions, and then you project it locally to a state of a lower dimension. This one does not violate, this one violates. So, this was an example from a higher dimension to a lower dimension, and this operation was a projection operator. You just project out some part. Gizon showed another example already in 2 cross 2. So this is a state rho in 2 cross 2. It does not violate a Bell inequality. And then he used POVMs, local filtering operations, to get another state, still in 2 cross 2 dimensions, and this one violates. This is all around 96, 98, this type of years. I forgot. This one is in PLA. These two I forgot.
Can you repeat the second example?
In this example, it's a state in higher dimensions, and where you can show that it has a local hidden variable description. So it will not violate a Bell inequality. But then you can use a projection operator to get sometimes some state, the local projection operator on one side, and you land in a state which will violate the inequality. Another inequality.
So can we ask, like, why is it happening, or what will be the consequences of that?
Well, so for example, what you can think of it is that a sub-ensemble of this is violating it. So if you use the ensemble interpretation of quantum mechanics, you can think of this state as a sub-ensemble of this state. And then that sub-ensemble is violating. You can think of it in these terms.
But the whole ensemble, the whole state is not valid.
The whole state is not.
There is a converse too. If I find a Bell inequality violating scenario, I can go to a higher dimension where it will not violate.
I mean, how will you go to higher dimension? This you will apply auxiliary systems.
Isn't this similar?
If the auxiliary system, I mean, the point is that a Bell inequality is anything that you can derive by assuming local hidden variables. So that, I mean, if a part of it already violates, even when you add these auxiliary system, you can apply only identity operators there, and then you will have violation all the time. So this will probably not happen. You have to think of how to formulate the problem. It's not clear to me how will you formulate it.
So the second case is not about the auxiliary system, right? We cannot treat
His problem, you mean?
Yes, yes.
Yes. So if
Generalization.
you just adding auxiliary system and applying identity operators will not work. We have to somehow formulate the problem in a better way. It's not clear to me how will you formulate it.
So using a POVM, you said whoever converted it into a state that violates it.
Yes.
So
So
the
this
entanglement
third
amount
problem.
changed.
This is by Gizon. Yes?
Entanglement amount did change.
Yeah. Bell inequalities are related to entanglement, but not directly. It's not clear how it is related. A separable state will never violate a Bell inequality. This is clear.
heuristic formulae that you said.
Pardon? Yes.
Yeah, so that is that a, like how much CHSH is violated? Is that a measure of any non-classical correlation?
It is not a measure of, in the sense it's not a monotone. If you want to use it as a measure, you can, but these measures of correlations, quantum correlations, would like them to be monotone. This is not a monotone.
So these inequalities are just qualitatively we can figure out whether it's non-local or not.
Whether it violates the local realism or not,
But not
or whether it is entangled or not. And currently they are used for giving you device-independent proofs of entanglement or device-independent proofs of cryptography, key distributions and so on.
But the question of locality is still not answered in that sense, using Bell inequality.
No, it only says that the local realism is violated. The conjunction of locality and reality is violated by quantum mechanics. It's to the converse. I mean, there is the Bohm model, which is a hidden variable model, which is non-local.
Sir, is it possible to quantify the violation of local realism by the amount of how it is, like the difference between the violation of the Bell inequality? Can you quantify that?
Yes, this is how it is done. In the sense, I mean, all quantifications are should have some sort of a monotonicity. That is what is missing.
But monotonicity is not.
Monotonicity is the thing that is missing. I mean, you should be. I mean, one has to somehow write down a resource theory out of it, and I don't know whether it has been carefully done. I mean, there are some people who have done these things,
2
but
cross 2 they do it.
pardon?
In 2 cross 2 they are.
In 2 cross 2 for Bell inequalities, is there a resource theory? I don't know.
Like the PPT criterion gives the eigenvalue, when that eigenvalue is treated as an entanglement measure.
Yeah, that is a different thing. That is not related to Bell inequality.
That is a monotone.
That is a monotone. Yeah. So we have entanglement measures. That is, the question is whether Bell inequality violation amount can be used as a measure of something. So there is, so we go away from this Bell inequality zone but still stay within foundation. There is something called a GHZ effect or the GHZ paradox. If you want the Grinberger, Hall, Zeilinger, so it is now in 3 parties. It again assumes, it's again a violation of local realism but in 3 parties. There is something called Hardy's non-locality or Hardy effect or Hardy paradox. It's again a violation of another way to show how quantum mechanics is inconsistent with, and this time this is in 2 cross 2. This one has a strange thing is that the maximally entangled state do not show Hardy's non-locality. Nobody knows why. Ramesh, who is visiting us, he has found a way to use Hardy's non-locality to give secret keys. In all the other, so this is also used to give secret keys, but in this case, it's the outcome of the experiment that is used as the keys. In his, it's your choice of between the observables at each side that is used as the key. I mean, there are other people in that paper, Ramij, there's Pavlovsky, there's some other people, I forgot them. He did it during his postdoc in Gdansk.
So these high dimensional states, rho,
Mhm.
are they entangled?
And they're all entangled. Otherwise, they will never violate Bell inequality. Any Bell inequality, any of these effects. They are all, entanglement is necessary, but not sufficient. And so this Hardy's non-locality shows it that entanglement may not be related to non-locality, or I know this non-locality, all these are within inverted commas. It means local realism. Hardy, I think, in his first paper wrote it like this, or maybe other people. But you see that the state that we claim to be maximally entangled for certain reasons does not violate this. You cannot show Hardy's non-locality for the maximally entangled state. This is analytically shown.
So what are we saying exactly? Violation of only realism? Like you said, Bohm's model is non-local but a hidden variable model. So it does not violate realism. Bohm's model.
It's not a violate realism. Yeah. So there is what all these things tells you is that if you try to find a hidden variable model for quantum mechanics, like we have classical mechanics for classical statistical mechanics, if you want to find an underlying theory for quantum mechanics in which you know, you don't know, but the system already knows in which one to click from before, then all those theories should be non-local if it has to be consistent with quantum mechanics.
Non-local in the sense, non-local as well as violate realism.
It's the conjunction that is violent. This is the point.
Yeah.
If you take a model in which the system is the realism is there in the sense that all the results of measurements are known, then the theory has to be non-local in this sense. And if you know that a theory which is consistent with quantum mechanics and it is local, then it cannot have hidden variables. Then you will not know all the results of measurements.
So in that first case, the first left-hand case, you said that like when we had just one state row, that was not violating Gauss inequality. So that's why maybe she asked like, does all these row correspond to states which are entangled?
Yeah, they're all entangled. So this is the same state actually.
Yeah, so you said that when just one state was there, then it was not violating Gauss inequality. That means it was not entangled?
No. This is the point.
There are entanglement.
Separable states never violate Abel inequality, but the opposite is not clear.
But that's also not certain that such states are entangled.
If you violate Abel inequality, it is certainly entangled.
Okay.
The opposite statement you cannot make.
Yes. So there is a gray area between those.
Is there any non-classical correlation other than entanglement?
Bell inequality is one which is stronger. There is the steering inequality violations that, so when a state is there is something called steering. When it is non-steerable, then it is, that's another thing. There is this discord and work deficit which goes into separable states. So if you think of this as the separable ball, then there are these non-steerable states that are, the steerable states are inside, but more than separable. And then the Bell inequality violations are bigger than that. And these are the ones that violate Bell inequality. These don't violate Bell inequality but are still entangled. These are steerable but entangled. These are separable. And then inside separable states, there are states which are classical. This is a set of measures 0 that are non-discordant, that has discord 0. So something called discord. We can come to it later on. There's something called work deficit, discord. There are many such measures which typically form. If the measure is 0, it typically forms a 0 measure. It's the 0 measure set of these, the 0 value set of these measures are typically 0 measure states. They have 0 volume. Pardon?
Can you repeat that?
So these measures which are beyond entanglement, like discord and work deficit, if you consider the set of states for which discord equal to 0 or work deficit equal to 0 and this type of things, then that set is always inside separable states, and typically their volume is 0. So yeah, you want me to define volume of a set?
Yes,
There is no
That,
finite neighborhood.
Pardon?
There is no finite neighborhood around those. this
Roughly,
model.
yeah. So a zero measure set, it's better to explain on a straight line. Then we can go to this. It essentially uses the concept of the metric. Yes, so you want distance. So on the straight line, any finite set has zero measure. So in the case of a line, volume is length. So we call something as a set of zero measure if it satisfies the following property. Is that you choose any epsilon greater than 0, then this set S will have some elements x inside it. I am trying to prove that S has volume 0 or length 0. This S is a subset of the real line. Then I will consider this the union of the lengths of intervals x minus epsilon, x plus epsilon, and I will call it L. Yes? Then what I want to show is that I can, for any epsilon greater than 0, I can always cover this S. So this is called a cover. So this set L contains the union of these intervals. Then this L contains this S. Yes. And now I find the length of L. So length of L is essentially the sum of these numbers. So it's the summation, but the summation is highly misleading. Yeah? There can be an integration. The summation of the lengths of these intervals. So I call it Lx. And this goes over X, where this X is an element of S. And then, if I can bound this length by an arbitrary epsilon greater than 0, whatever small epsilon I can choose, I can always find an L that contains this. Then I will call this as a set of measures 0. So I am covering the entire thing, and then I am squeezing the volume to 0. Such a set is called a set of measures 0. So examples will be any finite set, the set of rational numbers. These are a zero measure set. A set having a non-zero measure is any interval.
So set of irrational numbers, those are not.
It has the same volume as the real line, it's full volume.
So does a set of measure 0, is it always countable?
Not necessarily. Any countable set is the opposite is true. Any countable set is set of measure 0. So here the separable ball has a volume in the space. So when you consider when you try to speak of volume, you have to define the space. Yes. So let's say if you consider a patch on the floor, then with respect to this two-dimensional space, that patch has a volume. But with respect to the three-dimensional space, that patch do not have a volume. Yes, so one has to always define what is the space with respect to which you are defining the volume. So this separable ball has a volume with respect to the set of all states, all quantum states. But these states, so this is the state, this is the set that has entanglement equal to 0. This is the definition of the set. These are the states for which discord equal to 0 or some other measure. Those states in the space of states does not have a volume. That set changes from definition to, from measure to measure. Fine. Why did we were talking all this? Because of these sets.
Would you also draw bound entanglement
Pardon?
in this?
You want to draw a bound entanglement, you are welcome. It's better to go to another picture because the connection of bound entanglement with this is not very clear. So if you, this is your set of, this is your egg of separable states. So I am drawing it as an egg because these are convex. So, and this is the space of all states. This is the set of states that has positive partial transpose. These are separable. These are entangled, but if you transpose, then it will have a negative eigenvalue. It's better to say is not greater than 0. Negative has a different meaning. This means that it has a negative eigenvalue, at least one. And then there is another set. Nobody knows whether this set exists. Is that these states are distillable. So these are undistillable. Distillable means you take the state, you take many copies of it, and you try to create singlets out of it as much as possible. And asymptotically, you should reach to the singlet. The fidelity of the state where you go to the singlet should asymptotically go to 1. Those states are called distillable. These are the states which, so this entire class of states from here to here are bound entangled. They have entanglement, but they cannot be distilled. So if you want to create the state, you need entanglement. Once you create it, you cannot come back. Yeah.
Can you please repeat distillable?
So distillability definition is, there is an epsilon delta definition. I'm avoiding it. So what I'm trying to say is that you have several copies of the state and you try to produce via LOCC, by local operations and classical communication, a smaller number of states which will asymptotically become close to singlets. Asymptotically means for the large copy limit. If you can do that for a certain state, you call it distillable. There are states for which you cannot do that. Certainly from separable states you cannot go there. So these states are certainly not distillable. But there are entangled states which we know their existence. And you cannot, they are entangled, but you cannot distill them. But all the examples that we have of such states, bound entangled states, the states that are entangled but I cannot distill, have this property. Nobody has ever found out a state which does not have,
Greater than zero.
greater than, greater than 0.
So in PPT bound entangled states are
So these are states from here to here are the ones which has this property. This TA can be TB, it doesn't matter. So these are these states, these are NPPT, and these states are all these states up to here is PPT. This is PPT.
Entangled but not distillable.
Several states are also PPT. But there are states which are PPT but entangled.
What is the dotted boundary?
The dotted boundary is the boundary of undistillable states. I put it a dotted because of two reasons. One is I don't even know its existence. It can be this line and this line may be the same. And secondly, people have proven that if this thing exists, then it has to be non-convex. So that is why.
So there are negative partial transpose states which are undisclosed.
We don't know that.
PPT bound entanglement.
PPT bound entanglement. This set we don't know its existence.
You have examples of states which do that.
No, nahi hai. We don't know it.
Are you assuming that it exists?
I'm not assuming it
Well,
exists.
we don't know.
We don't know.
There is anything.
But people have proven that if it exists, it has to be non-convex. So you will find two states
Adding up.
here and here which has zero distillable entanglement, but you add them, you get greater than Z. On this side, you will land in here, you will have a state which has distillable
2
entanglement.
cross C3.
Pardon?
2 cross 3 dimension.
Yes. So it's a good point that if you are in 2 cross 2 or in 2 cross 3, this boundary, and this boundary, they converge. They collapse to one boundary. So in two spin half particles or one spin half and one spin one, all three boundaries collapse. There we know everything. So what does it mean? It means this PPT criterion is the separability criterion. It distinguishes between separability and non-separable states within 2 cross 2 and 2 cross 3.
Do we know that Bell inequality is always weaker than PPT?
In higher dimensions you're talking about, right?
Yeah.
In 2 cross 2 we know this. In higher dimension there was a conjecture that PPT states will never violate Bell inequality by Perez. I think that has been disproved by Vartesi, I think. I don't know that paper very well.
Bell inequality वाली line बनाने लगे तो उसके बाद
So what is the problem to generate that state, the non-existent state? Like if we randomly choose those parameters of those 3 cross 4 Hilbert space. Is it actually measure zero state? That's why we can't.
No, it's the well, we don't know whether it's measure zero or not. This PPT, this class doesn't have measure zero. This is not measure zero, and this class also has a volume. So I don't know, of course, but I mean, one would wager that even this will have non-zero volume. I don't know. Okay. So this volume question, of course, is the next step. I mean, we don't even know its existence.
Like varying the parameter, it's not possible to generate.
No. The point is the proof of whether a state is distillable or not is a very difficult question.
Sir, regarding that non-locality, so non-locality necessarily implies causality violation, no?
What is causality violation in this context?
You can find a space-like interval in which you can reorder the correlation between the two bodies.
So being entangled does not let you do signaling.
But non-locality will always imply causality violation.
So non-locality is only in the sense that a measurement choice here will change the measurement result there. This is the assumption.
If two things separated over a space-like interval can affect each other, I'm saying can affect, okay, entanglement, you said it is different, but if they can affect each other,
But they
then
will.
find a space-like interval.
No.
which you can-
But you don't have access to individual results.
Yeah.
You have access to only
Yeah,
averages.
but I'm not saying about the use of entanglement in that. I'm saying like in the Bohm's theory, you said
Mhm.
that is non-local.
But after you average Bohm's theory, you get normal quantum mechanics.
Average.
Because you will hidden variables are hidden. We don't know how to access it. So when you actually do your experiment, you want to get those go to measurements that you can actually do. So the things that are hidden, you have to integrate over them, and then you get normal quantum mechanics. So all the theories, all hidden variable theories must satisfy quantum mechanical, we have already done experiments, and the Bond rules seem to be correct in all of them. So any hidden variable theory has to satisfy that fact that all experiments done must be consistent with that hidden variable theory.
It should come down to quantum mechanics really.
Exactly. And in those cases, you have only average measurements, and those average measurements you cannot use signaling. Although there is a non-locality at the level of the hidden variables, it can't be used to signal.
At the level of the hidden variables, it is violating relativity.
The point is that you do signaling only you can observe. Only if you can observe. Something is going faster than light, that doesn't mean you are signaling. Signaling is there only when you can actually send some information from here to there. And so I recently read a joke which says that people are publishing so many papers that I don't know. So you know this.
Physical review.
So in physical review.
There is no information travel.
Physical review, the shelves are growing because the people are publishing a lot, and every month it is becoming bigger and bigger. And so after some time, of course, this will become very fast. So some time may come when it will go faster than light. But then that will not break relativity because there is no information transmission. It was by Richard Gill actually. I happen to know him. He's a famous person. He works a lot on the inequality.
Why are people sitting on physical review?
Pardon?
Why are people doing this on physical review? It's a decent journal.
Pardon?
Physical review is a decent journal, right? But why are people
People publish a lot these days.
Physical review is taken because it's sort of a big publication house. They just want to name one publication house. Yeah, okay. So I'm not going into these details. There are huge number of very beautiful partial results that are known in this scenario. Like for example, in 2 cross n, what is the result? Anybody knows? In 2 cross n, there is something known about bound entangled states. Is that there is no NPT bound entanglement. So this one and this one collapses to each other. In any, so 2 cross 4, 2 cross 10 or whatever you take, these two boundaries converge. So if you want to go beyond these two, then you have to go to 2 cross 4. In 2 cross 4, this set is there. This is known. And this part is not there. That is also known. So the first dimension, the minimal dimension where you can look for this is in 3 cross 3. There are 2 papers in the year 1999, one by the IBM group, another by Sirac, Levenstein and several others, and both the papers are claiming in different ways that they have some sort of evidence, they call it evidence, that NPT bound entanglement do exist. But nothing has been proven as yet. There are on and off people put papers on archive that it has been discovered, but these are all wrong as yet, and nothing bad in it. People are trying. We have 2 such papers from India, by the way.
By whom, sir?
One by Devashish Sarkar, another by R. Simon. There was one by Pavel Hordetsky as well.
About findings.
Pardon?
About findings.
He claimed that he found, but then he retracted it.
That is like MPPT is like a gap in the QIC standard model.
Yeah. But all these papers, what they do is that they essentially build the quorum in the subject. Yeah, I mean, you have more information. These are all wrong information, but some things. Every try, people get a new perspective of the same problem.
Those are available on archive.
Yeah. So you can retract a paper in the sense that you can say that this is wrong. It stays there. It stays there. You cannot take it completely out. Okay, so this was it, and there is also something called the Cochin-Specker theorem. That I will not go into. So this was about, so up to here everything we were talking about locality and realism. Cochin-Specker theorem talks about realism but replaces locality by contextuality, non-contextuality. Okay, we will go off from here unless you have something else to ask.
So can a witness distinguish between PPT,
Not here, but witnessing a bound entanglement is possible, yeah. So people's paper to look at is Otfred Guene and Lisa Toth, among others. There are many other people, but I am remembering these two, Otfred Guene, and there's something on this O as well, I forgot what, something like that. Anything else?
The existence of PPT bound integral state is already proved for general cross entanglement.
Yes, I will. There is actually there is something called an unextendable product basis. By using that, you can that is known to be there in all dimensions. That is not in this dimension. It is not there, but in all other dimensions it is there. And by using UPVs, you can systematically calculate bound entangle. Write down bound entangle state.
PPT bound.
All these are PPT bound. In 2x n you cannot use this, but there are other ways.
Because in 2x n the boundary is collapsed.
No, the reason why UPVs don't exist in 2x n, that's a different reason. The reason is that this is a product basis that is not distinguishable, and you can show that in 2x n all product bases are distinguishable. Orthogonal product basis. Anything else? So as I said that quantum teleportation is will go out of this so-called foundations region. So we have already discussed about quantum teleportation, which came in 1993. 1 year before that came quantum dense coding. Apparently this was known even earlier, but then the paper could not be published. And then Bennett and Wisner published it. It is also called super dense coding, and so the quantum teleportation is for using quantum channels to send quantum information, whereas this dense coding is a method of using quantum channels to send classical information. In both cases, beyond the classical limit. Yes. There is so all these channels that we were talking about, we did not concern ourselves with the security of the channel, in the sense that whether someone else can know what is being sent, and that of course is the subject of quantum cryptography. And there are other areas that concern it. And so one can say this is quantum cryptography without Bell theorem, because there is a quantum cryptography that uses Bell theorem to show something else. It's called the device independent cryptography. And the first was the BB84 protocol here, and then there was the B92 protocol. This is Bennett, Brassard, this is Bennett, and there is the something called a 6-state protocol. So the BB84 uses the 0, 1 and the plus minus states. This one uses any two non-orthogonal states, but better to use the 0 and the plus, let's say, and in the block sphere. This one uses 0, 1, plus minus, and also the y basis. Yes, all three bases. This was independently derived by Gison and difficult spelling, Beckman. There's an important paper by Mohamed Burenan, who derived the security proof of this. There's of course the general security proof by Preskill, Shor Preskill, for this. In this paper, they compare the security proofs of this and go to D dimensions. And you all know the concept of one-time pad that is used in everything. Fine. Pardon?
What is that?
You don't know what the one-time pad. One-time pad is, suppose you assume there is some way that the two people have been able to get hold of a sequence of numbers 0, 0, 1, 1, 0, 1, 0, something like that, which is the same as here. A long sequence, and she knows it, he knows it, nobody else in the world knows it. How it is created, that is the problem of key distribution. So all these protocols, they try to create such a sequence. The condition is that they have to be random, they have to be equal to each other, and nobody else in the world will know it. It's called the secret key. The way to do it, of course, one can create it by meeting. You create it and go away. And then there is, of course, the problem of how do you generate random numbers. That is a separate question. Suppose that is not there, we assume that you can generate random numbers. Then they can, of course, meet and generate it. The problem of quantum key distribution or classical key distribution is to generate them when they are far apart. So there are classical methods of doing it. That's how we do all our monetary transactions. And the way to do it in the quantum world is this. In the classical case, you assume that some math problem is difficult. There is a precise meaning of the difficulty. And in the quantum case, you assume that quantum mechanics is correct. And the one-time pad is the following, is that once you know that they are the same, then you have your method, you call this as B, this bit string, call it, I don't know, this S as the bit string. This S is the same, so this is the S. This is also the S. This string is known, this is secret, and is known to this person and this person, they are equal. And now, Alice now has a message that she wants to send to Bob, and we change it into bits. Everything can be changed to bits, all information. So you write it in bits, and then you term-wise add this M to the S. We're assuming that S is at least as large as M. This message, because this S is random, M plus will also be random. You add a random string to a definite string, it remains random. You publish it in newspapers. Bob reads the newspaper. He has S. Nobody else in the world has S. He adds S to it. This is one-time pad. One time why? Because it has to be used only once. If you have an S that you use twice, so suppose you publish this and you publish also this, then from the newspaper you can add these two. These two will get cancelled out. You will get M1 plus M2. Sum of two messages is certainly not random. It has a lot of information.
Yes, Schiller story, there was a frame like, certain holes in certain places. So, there was a copy and, there is a written letter. So, one just, places the card and reads,
Exactly.
it sounds similar to that, probably.
Also, multiple use can facilitate frequency analysis to crack the key itself.
Yeah, so all these are called, it has a name, so any method of jumbling up a message is called a cipher, and this type of ciphers has a name. It's essentially you replace something by something else. Instead of writing A, you write something else, some other letter, some number or something. All this can be broken by frequency analysis. Because, so there is actually a Sherlock Holmes story that it's called The Mystery of the Dancing Men. So there is actually frequency analysis that used to break the code. Okay, so out from here. There is, of course, you have realized that there is something called quantum cryptography with Bell theorem, and this was first given by Eckert. In 91 is called the T91 protocol. And initially it was thought that this is not so useful because if you can do cryptography without entanglement, why should I do with entanglement? Because it is anyway difficult to create entanglement. But then it was later on realized that this can be used, this protocol can be used to generate keys in a device-independent way. So that the point is that if you are buying the machines from somebody you don't have to, and the person says that you are measuring in the x direction and you are getting some results, but actually the operator may be actually measuring in the z direction. Independent of that, you don't have to believe in your devices, you will be able to get cryptography. And there is a variation of the Eckart protocol. Stop here, or you want to go further? On the next day, we will start with some algorithms, yes?
Next day is Monday.
Monday, will you be able to take?
Yeah, so I think we have to change the timing both for the RM and